Hey there, guys and gals. This is lesson 2 of unit 1 of Algebra 2, 212. We're going to dive right in. We're going to be talking about some properties of numbers, and we're going to be talking about sets of numbers, which is what we have on the screen right here. And then we're going to do an example, and then we're going to get out of here. So this should be review from Algebra 1. Let's kind of walk through what sets of numbers are, right? So what kinds of numbers can we have? We're going to start with the smallest set of numbers. That is the natural numbers. So what is a natural number? Well, natural numbers are also known as counting numbers. They're the numbers 1 through infinity. And they're no fractions, right? So we're talking about like 1, 2, whoops, I don't know what I did there. 3, etc., right? 4, 5, 6, 7, skip a few, infinity, right? That's where we're headed with natural numbers. Now, you may or may not remember whole numbers add one number to the natural numbers, and that's it. Whole numbers add 0. Okay? So it's 0 to infinity. Only whole numbers, no partial numbers. So 0, 1, 2, 3, 4, 5, etc. Right? Skip a few, infinity. Integers, now a common mistake, if you know what integers are and you're thinking in your head what integers are right now, it may be possible that you're thinking the wrong words. Right? Very, very common mistake that students will make is when I ask, what are integers? Well, the thing that they'll tell me is integers are negative numbers. Well, that is true, but it's only partially true, right? Because integers are both positive and negative whole numbers. So we're talking about like -2 down to negative infinity, right? And through positive infinity, a -2, -1, 0, 1, 2, etc., right? So it's worth noting here when we're talking about integers, the way that this is laid out is intentional, this graphic here, because all of the natural numbers are also whole numbers, and they're also integers, and they're also rational numbers. They're not irrational numbers. It lives its own. They're also real numbers. Every natural number is also an integer, but not every integer is a natural. No, I did that. This is the third time I've started this stupid video, and I said that I'd said it backwards last time too. Every natural number is an integer, but not every integer is a natural number, right? So it goes one way, but not the other way, right? It's kind of like saying that every square is also a rectangle, but not every rectangle is also a square, right? So integers are positive and negative whole numbers, right? Rational numbers are anything that can be written as a fraction. I'm going to take a brief aside to make a point. So anything can be written as a fraction. Okay. So what are irrational numbers? Well, you'll be tempted to say decimals, and you're not really right, but you're kind of right. So let me illustrate, and let's finish our discussion of rationals before we go on to irrationals. So rationals are literally anything that can be written as a fraction. So obvious things like 3/4. That's a rational number, right? Another thing that's also a rational number is any of these. So -16 is also a rational number, right? Anything that's an integer is also a rational number. Anything that's a whole number is also a rational number. All of those things. Also, 0.85. That's a rational number. Now, like I said, fractions. Well, that's a decimal. Well, fractions and decimals are the same thing. This can be written as a fraction, right? We can do 0.85 equals 85 over 100, right? So if it can be written as a fraction, then it is a rational number. So another thing that might be a rational number would be like 0.3 repeating. Now, so we're going to see in irrational numbers in a minute that some non-ending decimals are not rational. They're irrational. But if it is repeating, then it's also a rational number. Like in this instance, if we have 0.3 repeating, that can also be written as a fraction. It can be written as 1/3, right? So if it can be written as a fraction, it is a rational number. So then what are irrational numbers? Irrational numbers are things that are non-ending. Should that be hyphenated? I don't know, probably. Or is that all one word? I don't know. Hyphen, not hyphen, I don't know. Grammar for me, somebody else. Non-ending, non-repeating. And that's so the non-ending part does by itself doesn't work. But I'll hyphenate that one, then we'll cover all our bases. Maybe something's right somewhere. Non-ending, non-repeating decimals. So, examples of irrational numbers. The absolute classic example of an irrational number is pi. 3.14159, etc., 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 etc. Decimals that don't end and they don't repeat. Pi is a great example of that. Another great common example of that is the square root of 2. There's nothing. We don't have a rational number that gives us the square root of 2 or the square root of 5 or any of those things. Any square root of something that is not a perfect square. So the square root of anything with things like 25 or 4 or 9 or any of those things, those are all irrational numbers. We could also have Euler's number, which is 2.718, etc., etc., etc. It's a very important number in pre-calculus and in calculus and all these other things. In fact, in calculus, when you see a problem with E in it, you're probably happy because, spoiler alert, for the future of your lives, the derivative of e to the x is e to the x, right? So we like seeing those. That's something else. So there are quite a few different irrational numbers, but they are non-ending, non-repeating decimal numbers. Now you notice that the real numbers are all of the rational numbers and all of the irrational numbers. So that is, in fact, how the real numbers are defined. It is the union. Now, this is a sets thing. So all of this, rational numbers, we use the letter Q to represent those. I like to do mine when I write all of these letters. I'll go over what that means in a second. With kind of a double bar to represent that I'm talking about the whole set, right? So the union of the rationals and the irrationals. Right? So it's all of the rationals, so all of these and all of those, and that makes the real numbers. Now you notice these little symbols, all of these symbols, all of these letters represent this entire set. So we represent natural numbers with an N. And again, when I do those, I do it with a double bar. It just when I'm handwriting it, so it's different than just another capital N. Whole numbers also double U. Integers is a Z. Why is it a Z? I don't know why it's a Z, but it's not an I because I is irrational numbers. Rational numbers is a Q. Again, I don't know why it's a Q, but it's not an R because real numbers is an R. So those are all the different sets that we're talking about. Now let's talk about the properties of the real numbers. This is also probably review from Algebra 1, but here we go. We're going to dive in. Let me kill all this off, pull this up. So the commutative property. Oop. Thanks, Photoshop, for trying to think for me. All right, the commutative property. So these are all properties that are true for all real numbers. Everything. So whether it's rational numbers or irrational numbers, whatever, these properties apply to them. The commutative. What does it mean to commute? If I used to commute to work, I worked at 30 minutes away, and so I would move from one place to another place. And so that's how we remember what commutative is. Commutative is the fact that you can move variables around. Let's write this down in kind of math terms. The commutative property works for addition and subtraction like this. A plus B. And remember that we're talking about all real numbers, so these could be negatives as well, right? Is the same as B plus A. All right. So see how we moved those numbers over? So we move the two things. We can take things and we can switch places as long as the sign follows. That's important to keep in mind, right? It also works for multiplication division as well. So A times B equals B times A. And that's the commutative property. Really, really simple. So the next property we're going to cover is the associative property. If you associate with someone else, you are grouped with them. And so that's how we remember the associative property. We're talking about grouping symbols. And so the way we write that in mathy terms is A plus, I'm going to do parentheses, grouping symbols, B plus C is the same as if we grouped it this way. Move the little grouping symbols over to A plus B plus C. And if you notice, you kind of go back to the commutative property, look at your notes there, it kind of works the same way, because if we so we're basically just moving where the B is in the order, right? And so that's what we're doing there. As long as we keep the signs the same, we can move the way they're grouped. You notice these symbols are the same, so this does not work as A plus B times C. That does not equal A plus B times C. Those are not the same, right? So that symbols have to match. Now we're talking about addition. It has to be both addition, subtraction, or just multiplication, division. Let's add that to our notes. Actually, I'm going to leave that. You probably do want something like that. You may even want it cleaner on your notes as well. This is not it doesn't work if the symbols are different, but it does work for either multiplication or division. A times B times C is the same as A times B times C, right? So those do work, and that's associative property. Let's look at the next thing. Identity. So there's the identitive property of addition, subtraction, and the identitive property of multiplication, division. The additive identity and the multiplicative identity, right? So one's identity is who they are and their unchangingness. So for the additive identity, we're talking about what can we add or subtract from something and it stays the same. So if I have A, what can I add to A and it still equals A? Think about it for a minute. You got it? It's 0, right? If I take and I do A plus 0, it stays the same. So this is the additive identity. Excuse me. The multiplicative identity is what can I multiply times A, and it stays A, stays the same. A times what still equals A? Think about it. Okay, you got that one? What is it? It's 1. Anything I multiply times 1, it just stays the same. There's the identity. The next property that we're going to cover is the inverse. Okay, so the inverse is how do I get rid of or cancel something. We use this in equations all the time. I know you've used inverses in algebra, no matter what. If you've taken Algebra 1, you've used inverses, even if you didn't know that you were using them. So we still have A. Now we're talking about for the additive inverse, what can we add to A to make it go away? Turn into a Z. Oops, not turn into an A. That's the identity. Turn into a 0. So that's how we make an A go away with addition or subtraction. What can we add to A to make it disappear? Well, the inverse of A is the opposite sign. So if A was negative, the inverse would be positive. If A was positive, it would be negative. So we add its inverse and it cancels it, makes it go away. So there's also a multiplicative inverse. So if I have A and I want to multiply I times something, that's a little bit different because going away in multiplication, we end up with the identity is what we're going to end up with. See, the additive identity was 0. We want the multiplicative inverse to make this one go away. So we want it to equal 1. for multiplication division. What can I multiply times A to make it equal 1? Well, I have to multiply times the reciprocal, right? So I've got to flip it over. So it's got to be 1 over A, and that'll make it cancel, go away. So the next property is called closure. Now, this one you may not have seen before. So closure basically says if we add something to add a real number and a real number, then its answer is still a real number. So closure is, oops, I need me another layer. Closure says that if A and B are real numbers, then A plus B is a real number. We don't if we add two things in the universe, then we don't somehow jump out of the universe. That's essentially what we're saying there. It's if we start as real numbers, we're going to end as real numbers. That's what closure means in the mathematical sense. All right, the last property is one that you probably are familiar with. Everybody's favorite, distributive property, right? So, what is the distributive property? The distributive property looks like this. If we have a real number outside of parentheses, so A times B plus C. Now this actually is where, so this would be where we can't use associative property and regroup this as just the multiplication in the front, right? This is what I was talking about earlier. It was just kind of a preview. We can't do that. We have to distribute it, because what happens is that A has to get distributed to both. And so A times B plus C, and this, by the way, works even if it's more than just two, a binomial here. It can be B plus C plus D plus etc., right? Doesn't matter. Either way, if we have multiplication times a sum, then we have to distribute it, and it turns into A times B plus A times C. Right? That's the distributive property. All right, so those are all of the properties of real numbers. It's probably review at this point. I hope it is. If not, that's why we do review. Right? Let's do one example using some properties. We're going to take and we're going to simplify this expression. So taking a look here, we're going to simplify all this mess. So what do we have here? We have a couple of distributive property points, right? In this first one, we're going to distribute this 4 here. And this next one, we're going to distribute the -6. Now, I did this one very intentionally. It's very important that on this one here, we are distributing this -6, not -6 and then +6. So that's gonna change both of these signs, and that's really important that we follow along there and we do that right. Okay, so we distribute this 4 times -2a. 4 times -2 is -8. And then we've got times a, right? 4 times 3b is 12b. Okay. And we're distributing this -6. The -6 times 3a is -18a. -6 times -8 is +42b. Did you catch what I said wrong? I caught it, and I had to sanity check myself, make sure I was thinking right. That's incorrect. It is positive. It is positive, but it's 48b. I think I also said A. Oops, now I'm writing all kinds of things wrong. This video has been the bane of my existence. I've made all kinds of mistakes. I'm not restarting now. Not doing it. All right, so there's one more thing we can do to simplify this guy, because we have some like terms here. All right. Do you see where they are? So we have the A's in common, And then we have the B's. Oops. All right, so let's combine the A's. Remember, when you're combining like terms, all you do is you add the coefficients. So -8 and -18. So -8 plus -18 is -26. And we've got A, right? -26A. 12B plus 48B is 60B. So plus 60B. And that's all for that. That is properties of real numbers. We'll see you in class, or otherwise, if you're one of my students, see you in class. If you're not one of my students, thanks for joining us. Hope this was helpful. Let us know how we can help you with anything else in math or science or general homeschooling. Have a wonderful day. Bye-bye.